Okay, I'm going to go through the 10.1 quick check. Okay, first off, they said when I identify the type of bond and indicate charges if appropriate. Okay, the type of bond, we are looking for whether something is a metal and a metal. Okay, that's metallic. We want to see whether it's a metal and a non-metal, that's covalent, or non-metal, non-metal. I said that wrong. Metal, non-metal is ionic, and non-metal, non-metal, that's going to be covalent. And then of the covalent, we're going to have two different versions of that. So let's just do it. Here we have C and O. Those are both non-metals. So non-metal, non-metal, we know that's covalent. Okay, but then we have to go back and think, which ones are our strong non-metals? And the strong nonmetals are N, O, F, and Cl. So if one of these is a strong nonmetal, which it is, and the other one's not a strong nonmetal, so it's a weak nonmetal, then we know that this guy is polar covalent, PC. That means they're going to share but not share equally, and we're going to make the strong nonmetal a little bit negative and the other one a little bit positive, and we're using the small case delta. Magnesium, magnesium, that is absolutely positively metallic. Two metals are metallic. H and S, okay, H and S both are nonmetals, so we know this is covalent. N, O, F, and Cl, H and S isn't either of those, so they're both weak. So this is a non-polar covalent, meaning they're both going to share fairly equally. Okay, it'd be a tiny bit polar, but very, very equally. Okay, Mg and O. Mg is a metal, O is definitely a non-metal, so that's going to be an ionic. Okay, S and O, again here O is a strong nonmetal, S is a weak nonmetal, so this is going to be polar covalent. Two nonmetals make it covalent. Now since this is, I forgot one. Go back to here for ionic, okay, the nonmetal is going to be negative, a full negative, and the magnesium full positive. Now we know it's actually +2 and -2, but we're just showing that there is definitely a positive and a negative charge, not a partial positive negative. Okay, for S and O, we say that is going to be also polar covalent. The strong nonmetal O is going to be somewhat negative, and so the other one is somewhat positive, the weak nonmetal. And Fe and S, we got a metal, we have a nonmetal, so that is ionic. Okay, the nonmetal is going to have a full negative charge, and the metal will have a full positive charge. So that's the answer for the part 1. Okay, Lewis structures. We want to do these atoms and ions. Okay, well here we'll just put the symbols in first. Now this guy is an ion, so we're going to put on a symbol and charge, brackets, and same thing here. Okay, so carbon is in the 4th column if you look at your periodic table, so it's going to get 4 valence electrons, 4 dots. Potassium's in the first one, we're going to put 1 dot, any of the 4 sides is fine. Sulfur is in family 6, so it's going to have 6 dots. Okay, so that's going to be, okay, I'm going to make this a little bit bigger. So we're going to have 2 on 2 sides, we're going to have 1 on the other sides. Okay, just like that. If you did it 2, 1, 2, 1, that is fine. Okay, making these a little bit stronger. Okay, for oxygen, oxygen has 6, so I put 1, 2, 3, 4, 5, 6. But because it's 2-, then it has filled in, so it has 8 valence electrons. And aluminum usually has 3, but since it became a positive ion, it lost its 3 valence, so we just show no valence electrons. We know there are 8 in the next level down, but we don't draw any of them. Okay, Lewis structure of an ionic compound, okay, K2O. Well, we can see if we did K, we're talking about K plus and O2 minus. Okay, and we're going to have 2 K pluses with our O2 minus. So the way we're going to show this, we're going to do a K plus, and we know our positive ion loses its electron. We're going to have oxide, so it's going to look like this, and it's going to have 8 electrons, an octet, 2 minus. And then we'll put the other positive K on this side, because the positives would like to be near the negatives. And that would be our Lewis structure for the ionic compound. Now the Lewis dot structures for all these different covalent compounds. Okay, so carbon tetrachloride, the first atom almost always goes in the middle, and then we put the chlorines around it. And we start off and say, well, let's just give everybody an octet. And what that means is there's 8 electrons near each of these atoms, but some of these electrons, okay, I'm going to color them differently, like this pair like this, the bonding pair, that counts for both the carbon and the chlorine, which is fine. Okay, so right now everybody has 8 electrons, and that is the right number because carbon has 4, chlorine each has 7. Okay, and so that we've drawn 32, which is the right number. Okay, we'll try nitrogen. Okay, nitrogen would have nitrogen, we'll put it in the middle. Okay, we'll put the chlorines around it. Okay, we're going to begin by giving everybody an octet. And a lot of times that's the right answer. And it turns out it's going to be the right answer in this case as well. Okay, so nitrogen has 5 valence electrons. I'm going to color them in a little darker. And each of the chlorines has 7, which it can make one bond. So we can see each of the chlorine does have 7. So we have the right number of electrons. This is the right structure. Okay, OCl2. Okay, oxygen, okay, can do 6. So I'm going to do it like this, 2, 2, 1, and 1. That means there's one place on the right, one place on the bottom to make a bond. And if we remember our model kits, the oxygens were the red spheres that had 2 holes drilled in it. So here's chlorine. Chlorine has 7. 1, 2, 3, 4, 5, 6, 7. And here's chlorine. 1, 2, 3, 4, 5, 6, 7. So everybody here has an octet. And if you don't understand what I mean by octet, here, you can say here's chlorine, that's near 8 electrons. Here's chlorine, it's near 8 electrons. And here's oxygen, and it's near 8 electrons. Even though we're sharing some of those electrons, we count them twice, but everybody has an octet. Okay, F and Cl. Okay, F has 7 valence electrons, and chlorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Fluorine 1, 2, 3, 4, 5, 6, 7. And we can see everybody has an octet. So again, if we gave everybody an octet, then that would have worked. Okay, carbon dioxide, slightly trickier here. Now we're going to go carbon, oxygen, and oxygen. And what's going to happen is I would say, okay, let's give everybody an octet to begin. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. If I had enough electrons, that's what I would draw. But I don't. Okay, this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. But if I have 4 plus 6 plus 6, I really only have 16 electrons in CO2. So I need to save 4 electrons. So what I can do is take away a pair and take away a pair and put in a shared pair. So I can that's going to save me 2 electrons, so I'm now down to 18. And I can do the same thing again, take away a pair, make these share. So now I'm down to 16, which is what I have, and everybody still has an octet. So if I look at this carefully, that this oxygen is near 8, okay, this carbon is near 8, and this oxygen is near 8. Okay, so I'm going to redraw this down here at the bottom where it's a little bit cleaner. Okay, so CO2, carbon in the middle, double bond to my oxygen, 2 more lone pairs, double bond to my oxygen, 2 more lone pairs. This molecule comes up so much that I would just memorize its structure because you see it a lot. Okay, CH2O. Now it gets a little confusing. Well, how are we going to put our atoms? But, the C will be in the middle. And if we remember, when we were building models, that the carbon has to make 4 bonds. Well, it can only make 1 bond to a hydrogen and 1 bond to a hydrogen. So the other 2 bonds, okay, can be made to the oxygen. So we can see what happens is that, if we gave everybody an octet who wanted one, not hydrogen, but carbon and oxygen, then we could take away a pair from carbon, take away a lone pair from oxygen, and replace it with a shared pair, and we can get a double bond there. So this is the structure here, and this is formaldehyde, like they use for preserving things. Okay, C2H2. Okay, I have carbon and I have a carbon. Okay, hydrogens, there's 2 of them, so let's kind of put them out here symmetrically. And we're going to have to hook on that. Okay, well, what do we have left? Okay, is we have carbon has 3 electrons, I'm sorry. Okay, so we're actually going to use those to make 3 bonds between those 2. Now, if we were starting with an octet, I'd say take away a pair, make them share, and then do it again, take away a pair, make them share, and we end up with a triple bond. This is acetylene, a very good fuel, because there's lots of energy stored up in that triple bond. Okay, nitrogen and hydrogen. Okay, so what happens here is nitrogen has 5 electrons. Okay, 5 valence electrons, so does the other nitrogen. Hydrogen, okay, again, let's make it symmetrical. Let's put one on each side, and we know we need a pair of electrons there. Okay, well, nitrogen, okay, if we gave everybody an octet, then we'd say, okay, it goes 2 here, 2 here, and we have to have 2 here, 2 here, and 2 here. Well, what happens, that's too many electrons. I have 10, 5 plus 5 plus 2. I have 12 electrons, I've drawn 14. So I'm going to take away a couple of these lone pairs and replace it with a shared pair. And here I have a nitrogen-nitrogen double bond. Okay, here's hydrogen and oxygen. Okay, oxygen can make 2 bonds. So we're going to make one to hydrogen, we'll make another one to hydrogen, and then we'll make one between, and these have lone pairs on them. So again, if we were to draw this, we put the hydrogens have to go on the outside because they can only make one bond, and I gave everybody an octet who wants one, which is oxygen, then I actually have the right number of electrons, and that is the structure. That's peroxide, hydrogen peroxide. That oxygen-oxygen single bond is kind of easy to break. Well, here we have CH3NH3+. Okay, so this whole thing is going to be an ion, so I'm going to go ahead and put brackets in a charge before I forget. Now I have my carbon. Okay, it can bond to a hydrogen, and bond to a hydrogen. Then I'm going to bond it to my nitrogen, which is going to bond to a hydrogen, and bond to a hydrogen. Now let's check our electrons. Carbon has 4, nitrogen has 5. So if we have 4, we have 5, and we have 6 hydrogens. And because we have a plus charge, that means we're going to lose 1 electron. So when we get all done with this, then I can see I have 4 plus 5 is 9, plus 6 is 15, minus 1, 14 electrons. And I've drawn 14 electrons, 2, 4, 6, 8, 10, 12, 14. So this is actually the right structure. Okay, NO2 minus, that one is a little bit tricky, okay, because what happens, we say, okay, let's do our nitrogen. You know what, I'm going to come back, I'm going to do this one down here below. So NO2 minus, I need some room. So what I would normally do is say, okay, let's say nitrogen, and I'm going to put an oxygen and oxygen. So the first atom in the middle. Okay, now NO2 minus, that's 5 plus 6 and 6, okay, 12 valence electrons on the oxygen, and a negative charge means there's going to be one more. So I have 5 and 1 is 6. I have 18 electrons altogether. So I'm going to start by giving everybody an octet. And if I had enough electrons, that's what I would do. And that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons, but I only have 18. So I'm going to take away a pair, and make them share. Now I just happen to, and this whole thing is a negative ion, I just happen to choose my nitrogen with the right oxygen. I could have also chosen to do nitrogen with my left oxygen, and I would end up with a picture that looks like this. Okay, which is the same picture, only off the kind of a mirror image. And so what we say is going on is that there is resonance, that the actual bonding is a combination of these two, that both of these pictures contribute to the bonding. And this resonance idea has something to do with the fact that we are limited by this Lewis dot structure, okay, that we have to show it, we have to put those electrons in one place or another. And I'm going to use my shortcut here, okay. Now notice something, that when I have a situation where I have a single bonded O, I get 3 more lone pairs. When I have a double bonded O, I get 2 more lone pairs. And then that is going to resonate with nitrogen double bonded to the left, single bonded to the right. Single bond gets 3 more lone pairs, double bond gets 2 more lone pairs, and there's a lone pair on the nitrogen. And these two together, okay, give the structure of what NO2 minus is all about. Okay, SCl4, okay, sulfur. Now I know that it takes 1 electron from sulfur to hook on a chlorine, because I know chlorine has 7 valence electrons. So I'm going to need to use 4 of my electrons on the sulfur just to hook on those 4 chlorines. Now sulfur is in family 6, and I know that I have 6 valence electrons. I've used 4, so I have 2 more, and I'm going to put them here just on the central atom as a lone pair. And that's the picture for SCl4. So those are all the pictures for the different covalent compounds, and we are done with our quick check.